Welcome, everyone. We're here to talk about a major shift that arrived in Apache Spark 4.1, a new component in Spark called Spark Declarative Pipelines. I'm Sandy Ryza, a committer on the Apache Spark project and one of the main authors of this new component. I currently work at Databricks, and before that, I was the lead engineer on the Dagster data orchestrator. Spark Declarative Pipelines, often abbreviated as SDP, is a lot like what it sounds like. It's a declarative framework inside Apache Spark that makes it very straightforward to build reliable, maintainable data pipelines. SDP is built on top of Spark's other core components, Spark SQL, PySpark, and Spark Structured Streaming. It has first-class APIs in both SQL and Python, and it supports both stream and batch processing. We're going to be discussing SDP from a few different directions. We'll start with the 10,000-foot view, talking about Spark's high-level progression from an imperative to declarative approach to processing data. Then we'll talk about some of the challenges in data pipeline development and maintenance that motivate us to develop SDP. After that, we'll zoom into the core of SDP, its main abstractions for defining data pipelines. And last of all, we'll talk through how to actually use SDP, how to structure your code that defines your pipeline, how to run your pipeline, and how to interpret its output. So when we say SDP is declarative, what we mean is that the developer only needs to specify the what of their data pipeline, rather than focusing on the how. They define the data sets that they expect to exist, and the queries that describe those data sets' contents, and the framework handles the rest. This declarative approach isn't new or radical. You're likely already using it in your infrastructure and workflows today. For example, when you deploy containers with Kubernetes, you don't write imperative scripts that say spin up container 1, then spin up container 2. Instead, you declare your desired state in YAML. I want 3 replicas of this container running with these resource limits, and Kubernetes then figures out how to achieve and maintain that state. With Terraform, you declare your infrastructure as code. You don't write scripts that say create this S3 bucket, then create this IAM role, then attach this policy. You simply declare those resources should exist with these configurations. So just like Kubernetes manages your containers and Terraform manages your infrastructure, SDP manages your Spark data pipelines. Spark actually already made a big jump towards being declarative 10 years ago when it introduced Spark SQL and data frames. Spark SQL and data frames are declarative at the level of individual queries. However, as soon as you want to write more than one query, you'd be onto your own to figure out the execution plan. Spark developers have still needed to think imperatively when building a data pipeline. SDP changes this. It allows you to describe what you want, the tables and the data flows, and lets the framework figure out how to execute it, effectively extending Spark's declarative power from the query level to the entire pipeline level. To make this more concrete, let's look at an example of a data pipeline that's responsible for ingesting and processing data into 3 different tables. So the first is a table of raw orders data, which you want to hold in unprocessed order records from a Kafka topic. The second is a table of customers, which you want to populate from a CSV that's dumped out by our application database. And then finally, we want a clean fact table of orders, which contains a clean version of our raw orders joined with our customers' data. So having specified these tables and these queries that specify their contents, we have a full description of our data pipeline and how data should flow through it. In theory, this should be enough for some systems to just start running it and populating our data. In real life, though, this is historically just the start. To get a functioning data pipeline, we end up needing to handle all of these different pieces. So sequencing, executing all of our queries and making sure they run in the right order. Parallelism, if steps don't have dependencies on each other, we can make our pipeline complete much more quickly by running them in parallel. Retries, so if our query is reading data from a data source like Kafka, and the Kafka service is temporarily down, then our query is going to fail. But it might not fail if we try it again. So ideally, we wouldn't get woken up in the middle of the night to fix our pipeline if an automatic retry would have let it proceed. There's also error handling and validation. We need to make sure that each of the queries in our pipeline is compatible with the data that precedes and follows it. And last of all, dataset subselection. So what if we just want to update one of our tables without rerunning the rest of the pipeline? If we're writing this pipeline on our own, we have to figure out how to parameterize our pipeline and match table names to execution steps. So to accomplish these, it's common to end up with scripts that are fragile and contain a lot of bloat outside the actual pipeline logic. Evolving a pipeline to include new datasets or changing definitions of existing datasets becomes a fairly risky and heavyweight endeavor. So the basic idea of SDP is, what if you didn't need to do all this? What if you could just define what tables exist and the queries that populate them and have the framework handle the rest? By writing queries that read from upstream tables, you're already specifying your data dependencies. And these data dependencies determine the right order to execute in, as well as what can run at the same time. SDP analyzes your queries to discover these dependencies, and then handles executing everything in the right order for you. A core benefit of this declarative model is that it enables a deep, holistic understanding of your entire data pipeline before it starts executing anything. This deep understanding allows uncovering many errors early that you otherwise wouldn't be able to find until much later. So it analyzes each query and then uses the result to determine what columns and data types are expected to show up in the table that the query populates. It then uses that result to analyze queries that read from those tables and make sure they'll be able to execute successfully. So this cascading analysis approach ensures that everything matches, that upstream tables contain the columns and data types that downstream queries expect. This pre-validation step provides immediate feedback on whether the pipeline can run successfully, instead of you having to find out after a bunch of queries have already been executed, which can be very expensive and time-consuming. SDP also handles state management. So in imperative Spark, you have to manually specify checkpoint locations to manage streaming data, but SDP automatically assigns and manages the checkpoints for streaming tables, treating state as an intrinsic part of the pipeline. And then SDP also manages parallelization. So to run independent steps simultaneously in a standard script, you have to write fragile Python multi-threading code. But this SDP grasp analysis step can automatically do this parallelization for you. So that was the 10,000-foot view of SDP. Let's now start getting into the details of SDP's core abstractions. Ultimately, a data pipeline has just a few core building blocks. The first two, datasets and sinks, are the targets that your pipeline writes to. A dataset is a table or view, and a sink is a grab bag for any other kind of target, like a Kafka topic. Flows are the descriptions of the data transformations that populate these targets. Flows are typically defined by queries, so we sometimes use the term query and flow a little bit interchangeably. SDP offers us a few kinds of datasets. So these dataset types are linked to the kinds of flows that populate them, which we'll talk about kind of interleaved. So the first is streaming tables. A streaming table is a table whose contents are populated by a structured streaming query. Second is materialized views. You define a batch query, and the view is fully overwritten to match that query's result. Third, common views. These are just standard SQL views whose definitions are updated whenever you run your pipeline. And then finally, temporary views, which represent internal logic that's reusable within your pipeline. If you're using SQL, you're defining your datasets using SQL statements. And if you're using Python, you'll use SDP's Python APIs, which live inside the PySpark.pipelines module. It's common to alias this module using the abbreviation DP, or STP, similar to how the PySpark SQL functions module is often aliased to just F. This just makes you have to type less. Many of these APIs are decorators. They decorate a Python function that returns the data frame that describes the data flowing into the dataset. By default, the name of the decorated Python function becomes the name of the target table or view in the pipeline. So for example, in the code pictured here, the materialized view would be named events. So now let's break down these dataset types in more detail. As I mentioned a minute ago, a streaming table is a table whose data flows in from a streaming query. So if you're familiar with Spark structured streaming, you'll recall that a streaming query is just any data frame that reads from a streaming source. Streaming queries are incremental by definition. Each time they run, they process any data that arrived in their streaming source since the last time they ran. SDP currently only supports the append streaming output mode. That is, the results of the streaming query will be appended to the target table. You can see examples of how to define streaming tables here in both Python and SQL. In Python, we use the table decorator to decorate a function that returns a data frame. And in SQL, we use the create streaming table syntax, along with a select statement that defines the query. Streaming tables can read data from any Spark structured streaming source. So that means they can read from Kafka, from upstream tables, from directories of files, and so on. Streaming tables are especially useful for data ingestion, handling the bronze layer of raw data at the beginning of a pipeline before any filtering or aggregation happens. Another kind of SDP dataset is a materialized view. A materialized view is a table that contains the results of a single batch query. Unlike with a streaming query, where results of each execution are appended to the table, the contents of a materialized view are fully replaced by the results of the query each time the pipeline runs. Materialized views are often used for data in the later stages of a pipeline. Materialized views have a couple advantages over streaming tables. So because they're populated by batch queries, the programming model is very straightforward. You just write a standard select statement or return a standard data frame. You don't need to think incrementally. When doing joins or aggregations, you don't need to deal with streaming concepts like watermarks. Second, understanding their contents is very straightforward. Their contents are just the results that you would have seen if you executed your select statement or data frame. If you change your code and rerun your pipeline, the contents will purely reflect the results of your latest code. That's different from a streaming table, which keeps rows from previous executions, which might have used old versions of your data processing logic. The biggest trade-off, though, is cost and latency. Using a streaming table guarantees strict incremental processing. You only process each input record once. On the other hand, refreshing a materialized view often means rescanning much or all of your input data. So another kind of SDP dataset is a view. A view is a standard database view. It's a stored SQL query that can be referenced like a table. Unlike a materialized view, whose contents are updated when the pipeline runs, a standard view's contents are evaluated at the time that some other processor reads them. This means that it's always 100% up to date, but it also means that reading from a view can be slow and expensive. Because views contain no data themselves, all that happens when you run a pipeline with a view is that the definition of the view gets updated to reflect the definition that's in the pipeline's code. Views are currently only supported in SQL, not Python, just like elsewhere in Spark. The last dataset type is temporary views. A temporary view is like a standard view, but it's only visible within the pipeline. Temporary views are useful for centralizing logic that's common across a set of transformations inside a pipeline. So when you find yourself repeating the same logic over and over in multiple queries, stick it in a temporary view and read that view from your other queries. Unlike standard views, temporary views can be defined in both SQL and Python, and they can contain both batch and streaming queries. Finally, there's one other kind of object that a pipeline can write to, which is called a sink. A sink is a grab bag for any other kind of place that Spark streaming can push data to. So if you can write to it with Spark's WriteStream API, you can write it to a sink. Probably the most common kind of sink is a Kafka sink, which is used when you want your pipeline to write to a Kafka topic. Sinks are currently only supported with Python and don't yet have a matching SQL API. Aside from datasets and sinks, the other main entities in pipelines are flows. A flow is the fundamental unit of data processing. It reads from a source, applies logic, and writes to a target. In many cases, flows are implicit. So the datasets that we talked about earlier actually had implicit flows attached to them in most cases. When we use syntax like create streaming table as select, we're defining both a dataset and a flow that writes to it. In this case, you don't even see the word flow in your pipeline code, although you will see it in the logs when you run your pipeline. This flow started executing, completed executing, etc. The flows can also be defined explicitly. For example, this code up here that first defines a streaming table and then creates a flow that targets it is equivalent to the create streaming table as select syntax that we covered before. But why use the more verbose syntax when you could use a simpler one? One of the main cases for defining flows explicitly is to allow multiple flows to write into the same target table. Maybe you want to fan in data from multiple sources into a single table, and maybe you want these data sources to be able to be updated on different cadences, and you want to be able to just read from one at a time. The other main use case is to write to sinks. To use a sink, such as a Kafka sink, you first define the sink, and then you define a set of flows that write into it. So those are the core entities. When you define a set of datasets, sinks, and flows, you get something that's a little richer than the sum of its parts, a data flow graph. The nodes in the graph are these entities, and the edges are the data dependencies between them. So that was an overview of the main SDP concepts, as well as what the code looks like for defining them. To use these to develop and execute a data pipeline, you need to do a couple things. You need to put your code in a place that SDP can find it, and then you need to tell SDP to execute it. So let's break down how to do that. The main way to do both of these with SDP is via a command line interface named Spark Pipelines. The Spark Pipelines command offers subcommands for initializing a pipeline project as well as executing your pipeline. When starting a new project, you'll first need to create it with the init command. This generates the SDP directory structure with a default YAML config as well as a subdirectory to hold your code. That subdirectory will be populated with a couple example definitions that you can adapt to your use case. The configuration file is a YAML formatted specification, usually named sparkpipeline.yaml, that tells the runner where to find your code and how to run it. At execution, the Spark Pipelines command will automatically look for a YAML file in your current or parent directories, or you can specify a custom config with the -- spec option. Before executing the entire pipeline, you can use the dry run argument. As discussed before, this is where the shift left capabilities come through. This is your validation step, and it's one of the most important commands you'll use to prevent wasted time. When you run Spark Pipelines dry run, it compiles your entire pipeline graph and checks for errors without actually touching any data. This catches problems early, things like analysis errors where you're trying to select a column doesn't exist, graph errors like circular dependencies between tables, and even basic syntax errors in your SQL or Python. Catching these issues at this stage saves you a ton of time and headaches down the road. Once confident, you can then use the Spark Pipelines run command to actually execute your pipeline. And once execution begins, you'll see progress updates and live logs streaming to your console as each flow executes. As we mentioned before, instead of requiring users to define dependencies, like let's say Airflow does, SDP infers them from the queries. So the runner loads all the .py and .sql files and analyzes the data frames to understand input-output relationships. You're not responsible for putting files in order or mushing everything into one file. You can just have each transformation and each data set in its own file. You can see how the logic defined on the left side here maps to the graph on the right. Once the run is complete, SDP guarantees that the upstream tables exist before downstream queries start. And instead of manually defined parallelization code, independent steps are executed in parallel automatically. The Spark Pipelines CLI also supports a couple other useful options. So one of them is refresh selection. Sometimes you just want to refresh one or a few of the data sets in your pipeline without running all of them. You can supply a comma-separated list of data set names, as well as sink names to SDP, and it will execute a run that just updates those. The other is full refresh. So we mentioned earlier that streaming tables are updated incrementally, i.e. that only new data is processed on each run. But sometimes you need to truly start from scratch and reprocess all of your data. Full refresh allows you to do this. You will wipe out the contents of your streaming tables and streaming checkpoints and process your data from scratch. You can either refresh all of your tables by using the full refresh all option, or you can full refresh just a subset of them using the full refresh selection option. And so that's SDP in a nutshell. I'm now going to hand it over to Lisa to do a demo.
Hi, everyone. I really want to show off what it looks like to actually work with Spark Declarative Pipelines today in this demo. So first thing that we're going to do is using my Lakehouse stack at home, I want to show you the services that I'm running. So we can see that Spark is running, Spark 4.1, as well as Kafka and SeaweedFS and Postgres, just so that we have some batch and streaming analytics. In a Docker container now, I'm going to be looking at running Spark 4.1, spinning that container up, and then running Spark pipelines in the init command that you can see at the bottom. And then I'm going to pass in the name of the project called my pipeline. So this is going to start running, and then you can see the pipeline project has been successfully created, and that we can use Spark pipelines run to actually run the pipeline. Now we're going to continue looking at what happens afterwards once we get through this. Now we're going to use Docker to execute through the Spark 4.1 container, which you don't need if you have Spark just installed normally, to actually look at what files are generated. So we can see that there's a YAML file and transformations that were generated. And then we're going to see what it looks like to actually interact with some of these. So luckily, this means that our init command did work and we're able to successfully generate the files. Now we're going to look at the configuration file. It's very bare bones right now and just has the name, the storage path, as well as some of the libraries and globs, and what it will include as default. Now we're going to look at some of the scripts that are going to be contained in transformations. I've created a sales pipeline here, just a Python script that has some of this code, and you can see that it's taking in through an SDP pipeline, of course, importing PySpark, and then using the pipelines as SDP here. And then we're ingesting through a streaming table some Kafka topics that are including some orders, so some of these events. If we look at this with syntax highlighting, which makes it way easier to understand, we can see what this looks like. So we're defining the schema here, and then we're also reading the stream and then passing it into a streaming table called silver layer, and then the order stream. Next, we're going to create a materialized view here, and then we're going to see what this looks like. This is going to be ingesting data directly from Iceberg tables that we have that are sitting on top of SeaweedFS as our object store. This is all locally hosted, which is really awesome to see. And then next, if we go back to our shell, we can then try a dry run to see if this script actually executes, and then see what happens. So when we do a dry run, like Sandy mentioned, we're actually running everything at first without actually processing any of the data, which makes it really cheap and easy. And it helps us allow us to see if there's any dependency issues that we might have. We can see that the run completes and that it actually does create the data flow graph. Now, if we look at this new demo, we're going to have the exact same pipelines project with the exact same file and logic, but we're going to actually make a typo within one of the orders tables that we're trying to ingest within our batch pipeline. So if we go back to our sales pipeline now, we can see that we have a dedicated broken file for this so that we know exactly what we're working with. We can see that it's the exact same script, except one thing's been changed. We're actually using orders with a Z instead of an S. Now, if I actually try and run this again, running this through my Docker container containing Spark 4.1, but you can run this however you want, as long as you're running Spark 4.1, because that's where SDP is, we're going to see what it looks like to actually execute the dry run now. So using Spark Pipeline's dry run, and then our pipeline project, we're going to see what actually happens with the CLI. Now, we're going to be using the version of this pipelines project that actually has the broken pipeline loaded in. We can see that this is running now, and then we can see that some errors are actually popping up. So we can see that it first starts by creating the data flow graph. And then there's actually an error that's been raised where we've failed to resolve the flow in this Iceberg gold table. And this is because the orders table cannot be found. And you can see the rest of this is pretty easy to ingest, at least as a human. I can understand this message pretty clearly, that the flow failed to resolve because it contains errors, where the flow errors are, and then that this is an upstream error that occurred. Well, that's the demo. It's really easy to actually look at some of this. If you want to check out what this demo is, we'll put in a link in the description so you can try it out yourself. Thank you so much, Sandy, for that amazing presentation, and I hope you enjoyed that demo. So Spark Declarative Pipelines is one of many features that have been included in Apache Spark 4.1's release. So for 4.1 release, this is actually a huge release with tons of quality of life features, tons of big features as well, especially if you're a Python user, but also if you're a SQL user as well. So if you want to check out more, check out the release notes because there's tons of goodies in there and you don't want to miss out on a bunch of things that could be there. Another really big improvement there is real-time mode, which has been introduced with Spark Structured Streaming. So again, if you want to check out more, you can just Google Apache Spark release notes and check out 4.1. If you want to join our community, if you want to start a repo, check out the GitHub and then make sure that you're part of the dev list or the user list on the Apache website. You can also go to our community links as well if you want to engage with us. But also, we have a LinkedIn page, we have this YouTube page, Twitter/X, whatever it is that fits your fancy. And if you enjoy this kind of content, let us know. Subscribe and like if you like this content. And then also comment if you want to see other types of videos as well. Thank you so much.